A robot can unscrew a light bulb with 92% success, screw it back in and it fails 64% of the time. Same robot, same bulb. Why does taking something apart feel easy while putting it back together is a nightmare for AI? This is Gemini Robotics 2, Google DeepMind's new unified brain for humanoid robots. Here's how it coordinates the whole body, why the unscrewing demo hides a massive dexterity gap, what the real bottleneck is, and why you can't buy this yet. You probably think a 92% success rate means these machines are ready for your kitchen. They're not. The truth is weirder. And the numbers you saw are only half the story. Think of the old way of controlling robots like a conductor shouting separate orders to every instrument. Gemini Robotics 2 is different. It's like a jazz band where everyone listens to the same rhythm and improvises together as one unit. First, the stack isn't a single brain. It's 3 specialists working at different speeds. The VLA model turns what the robot sees into motor commands. That's the doing layer. It learns to predict movement from visual data without hand coding. The ER model plans multi-step sequences. That's the thinking layer. And on-device 2 runs locally on the silicon. That exists because factories often have poor connectivity. A cloud round trip introduces latency that can cause a fall. Running locally keeps the robot safe. If the network drops, the robot doesn't freeze. It keeps moving. This isn't just about speed, it's about safety. A lagging command could mean a dropped object or a collision. But splitting the brain creates a speed problem. Planning can afford to deliberate. Balance cannot. Balance is continuous, so the doing layer has to keep answering while the thinking layer is still deciding. When the plan meets the world, that gap is where the wobble comes from. Here's what that looks like in practice. They gave an Aptronic Apollo 2 humanoid one sentence. Put the watering can into the green bin on the bottom shelf. It walked across the room, crouched, picked it up, and placed it. No script for any of that. Version 1 would have stopped between each step because walking and reaching were different systems. And V2 adds something version 1 couldn't do at all. Multiple robots working the same space, sharing where they are and splitting the job in real time. Second, this is what whole-body intelligence actually means. It's not consciousness, it's feet-to-fingertips control. In older systems, a robot used one algorithm for balance, a second for the arm, and a third for fingers. These systems often conflicted. They'd freeze or topple when trying to do 2 things at once. Gemini Robotics 2 flattens that hierarchy. It removes the boss algorithm. Every joint talks to every other joint simultaneously. The model learns that shifting your weight changes your grip. It learns that crouching changes the angle required to pick up an object. It treats the whole machine as one continuous problem. You're no longer programming isolated commands. You are giving it a physical intuition for how its entire body interacts with space. In a second, I'll show you the benchmark table that reveals the brutal asymmetry hiding behind these numbers. Third, the numbers reveal a brutal asymmetry. The 92% success rate applies to unscrewing a bulb. That's mechanically forgiving. You can apply inconsistent torque and the bulb will eventually loosen. Screw it back in and the success rate drops to 36%. Picking an object off the ground is 45%. Sealing a zipper bag is 40%. This isn't a lack of smarts. This is the brutal math of friction and force. Friction isn't just resistance, it's a variable the model has to predict in real time. The gripper slips, the angle shifts, the force spikes. The model has to adjust before the human eye even registers the flip. Insertion requires precise force alignment, consistent pressure, exact rotational coordination the moment grippers touch the threads. Tolerance for error vanishes. Removal tolerates error. Insertion demands perfection. The system is slow. It hesitates in contact-rich scenarios. DeepMind itself describes true dexterity as a distant goal. And once you see why insertion breaks the model, you'll understand why this isn't coming to your home anytime soon. Fourth, the access reality. The platform is early access for partners only. You cannot buy the system. The hardware requirements are demanding. Factories run on legacy infrastructure with limited bandwidth, so the robot can't offload the heavy lifting to the cloud. It needs significant onboard compute to handle the model locally. That means the robot carries its own heavy silicon, driving up cost and power consumption. This hardware reality, combined with the need for industrial-grade durability, keeps the price tag out of reach for consumers. The inference times still lag behind real-time reflexes. The robot does not move with the instant adaptability of a human. It calculates, predicts, and executes with a delay that feels robotic, not human. Access is restricted to research partners and enterprise developers. Google is not shipping consumer robots. There is no timeline for a mass-market rollout. The catches are not failures of ambition. They are the actual boundaries of current physical AI. One more thing, and it's the part that'll matter longest. Over the next year, you're going to hear whole-body intelligence attached to every humanoid demo that gets posted. Most of them won't be doing it, so here's the test. If a claim would still be true with the robot standing perfectly still, it's not about whole-body intelligence. The term is specifically about what happens when moving and manipulating stop being separable. When crouching changes your grip, and gripping changes your balance. A robot with brilliant hands and a separate walking controller is not doing this, no matter how good the clip looks. That's the difference between a demo and an architecture. The 56-point gap between unscrewing and screwing isn't a failure. It's a map revealing exactly where the next wave of research must go. The breakthrough is the unified control that makes the gap measurable in the first place. It proves we can coordinate the whole body, even if the hands are still learning the physics of tight tolerances. The foundation is laid. Now comes the hard part. Solving insertion means solving the physics of how forces transmit through compliant objects. That is the frontier. To recap, Gemini Robotics 2 uses a 3-model stack instead of one brain. It achieves whole-body intelligence by coordinating feet to fingertips. It reveals that insertion tasks are the real bottleneck, with a 36% success rate compared to 92% for removal. And it remains an early access platform for partners rather than a consumer robot. Here's the takeaway. Whole-body intelligence means the robot controls its feet and fingertips as one unit, and the hardest part of robotics isn't moving. It's the messy physics of insertion. If you want AI explained without the hype, subscribe. That's what we do here, daily. That's the full picture. If this made it click, tap subscribe. There's a new AI explainer here every day, and tap the video on screen to keep going. See you in the next one.